Answer any question on my discussion board as we prepare for exam one. This question is a true-false question about understanding the TNB frame. And so I just want to recap the picture in our mind when we study 3D motion is this. So you've got some sort of curve, and then I'll show 3 examples, and I'll label, these are examples from class, and I'll show you those animations again. But imagine you have the derivative. Now the derivative vector looks like its tangent. Looks like this. A moment later, it might look like this. That's the derivative. That's r prime. At a given moment, we have this other vector that points the same way, which we call the unit tangent. I'll draw it right next to it. The only reason we use that is if we want to measure just the curve. So sort of certain situations when you want to measure the motion, where you'd want r prime, and certain situations when you want to measure the curve itself, that's when you want to do t. So like when we tried to study curvature of the curve, we used t. We found out that if you took the derivative of t, you got a vector that pointed inward. And if you make it a unit vector, it's what we call the unit tangent. We didn't do a lot with that in our course this term. We didn't have you compute it because it's kind of messy, but it's an important measuring stick. The picture always looks like that. So there's certain things that are always true. R prime and t point the same way. So they are parallel. T and n are always perpendicular. They're orthogonal. Because of both of those things, you could also say that r prime and n are orthogonal. So if you ever get a true-false question here, probably one of them is immediate. Like this is immediately true. Now I think the original question the student was asking was, I had a note next to this that said, in the other version, these were swapped. I had multiple versions of the test. That does not mean the true-false is swapped. It just means the location of those 2 questions was swapped. I made that note because that quarter, students were, I was like, don't come complaining about the true-false. Make sure you look at your version. So I apologize for the confusion on that. So this is true. R prime is always perpendicular to n. Now this is definitely false. You cannot say really anything about r double prime except that it's on the same plane. So r double prime is going to depend on whether you're speeding up or slowing down. So back when we talked about this, the reason that is because it measures the change. So if a moment later you are going much slower and then you go to measure the change in your velocity will be this. And if you take that vector and draw it back here, it'll be like this. That's where the second derivative will point. That's why it will point backwards if you're slowing down or forwards if you're speeding up. Now here are 3 examples from class. We use this to think about acceleration. So here was an object thrown in the air. That was my first example from class. And I said, here's the gravity vector. That's our acceleration, and it wasn't changing. When the object is on its way up, it's slowing down. And we called this the tangential component of acceleration, and we called this the normal component. The tangential component is going to be negative because you're slowing down. And we talked about how that's the derivative of the speed, and this is the curvature times the speed squared. What's nice is it still works in 3D. All of these vectors actually are on the same plane. We call the osculating plane. Here I've drawn the osculating plane. So basically any 3D problem you kind of think like our 2D. So here's another projectile problem, this one over here. And just to label a few things, this would be the tangential component of acceleration right here. How much we're accelerating in the direction we're going. And this other one would be the normal component of acceleration right here. That's what that is. So useful numbers to measure acceleration. So they're always in the same plane. So here's another one. The acceleration vector is way back here, which means it's slowing down. If you projected, let's label those as well. The tangential component, you'd come straight down onto this line. That's the tangential component. And the normal component is this way. Now, I'll just finish this by showing you those. So I haven't circled it yet, but you should know that this is false. Why is this false? Because you don't know which direction this points. It is not always parallel. Here are 3 examples where it's not parallel. Okay, let's finish with some visuals just because it's fun. Make it so you can see this. Let's make this nice and big. So here is an example with sort of all the pieces put together. The acceleration is down, the normal vector is inward. So the blue vector is the derivative, the red vector is the unit tangent, the orange vector is the unit normal. And you can see how they're useful measuring tools as we watch an object thrown. I made this so that I could like tweak the initial velocity. I showed this in class. You throw something in the air at some initial velocity, and you can let it go. So you can see there's a certain moment. Let me slow that down. There's a certain moment along the way. So initially it's slowing it down a lot. You can see that. It's way behind the normal, and I've drawn the little projections so you can see them. Then there's one moment right there where it was pointing the same way, and then now it's speeding up on its way down. So those vectors are very useful for thinking about motion. Here's this 3D projectile that I did in class, or I showed in class. Same thing. You throw it in the air. It's following that direction. T and N are there to help us visualize. Notice that T and N are always perpendicular, and the acceleration is that other vector. Altogether, it's very useful in my mind to be able to realize they're all on the same plane. So in this sense, this turns it into a 2D problem. It allows you to think about your motion. It works for more exotic things. Here's something that's slowing down a lot. The blue vector is the second derivative. That's it. All right, hope that's interesting.